I've been talking about energy, which is one of those truly important concepts in physics and in all of science. And in an example I just did, which, by the way, you should probably watch that video first. In an example I just did, I talked about how do I use conservation of energy to solve a question about a block sliding up a ramp. In particular, I had taken this block of mass m, 0.1 kilograms, pulled it backward against a spring for a distance of 5 centimeters from the spring's natural length, the spring at 150 joules per meter squared spring constant, and then I let go, let the block slide up, and I asked, how far is it going to go before it reaches its highest point and slides back down? What's that distance it's able to go? I asked that question. We solved using conservation of energy. We identified a system. We talked about the forms of energy that were relevant for that system. We wrote down equations for those forms of energy, plugged in a bunch of initial and final data to at least the zero parts to simplify the equation. We convinced ourselves the external forces in the system would provide zero work in this case, which is an important point. And then we were able to solve and find the solution, find what that answer to our question was. So we had done that. We got a distance of about 1.6 meters. So this time, I want to just make the smallest change to this setup. I want to know, what if instead of just a long ramp and knowing how far is this going to go before it reaches the end, I want to know, what if there was an actual barrier, some sort of barrier that was located a distance d equals 1.1 meters away from where I started. Same story, let's see, d equals 1.1 meters away, got that. Same story, but this time there's a barrier in the way. I want to know how fast I'm going to be moving, or how fast the block is going to be moving when it hits the barrier. That's my question. So to do that, we're going to see, what's that mean? That means that a lot of what we just did in the previous example is going to carry over exactly the same way. We're going to analyze using the same system, the block plus the earth plus the spring as our system. We're going to you have the same expressions for the forms of energy that are relevant in the system. Our initial data is even exactly the same, right? I started by pulling back, same 5 centimeters, same v initial equals 0. The initial stuff, we're still going to choose z equals 0 to our initial height to make life easy. So all our initial setup is the same. For that matter, the external forces are also the same, right up until the moment before we hit the barrier. Once we hit the barrier, all bets are off. But what I care about is the moment before we hit the barrier, what's my speed? So no new external forces yet. So that means same list of external forces and same conclusion that there's no total work done, that as far as energy is concerned, this is an isolated system. How do I solve differently? What changes in this case? Well, this time I can't say v final equals 0 because that was only true for the first question, how far would it go without a barrier? This time the different point is d is known. That distance d is a known thing. And so, just as I saw before, maybe I should have written this over here, that z final is equal to d times the sine of theta. Because I know d, my z final is now, I know d and I know theta, my z final is now a known quantity. That's something that's a known thing, and I'm solving for my final speed. So I guess the only difference this time, my spring is still unstretched at the end, so my delta x final is still 0. The spring still reaches its unstretched length at the end. But this time, instead of my 1 of mv squared being 0 at the end, this time v final is in fact my unknown, the unknown I'm solving for. That's my goal, is to find v final. But again, this is a straightforward question at this point. All I need to do to solve is just solve for that one thing. So for solve, when I look at this, and remember, we figured out before that the work was 0, the work due to external forces was 0. So all I have to do is get this 1 of mv squared on its own on one side first. So I'm going to subtract mgz final from both sides. I will get 1/2 k spring, and my x initial is L, remember, L squared, minus mg, and my z final was this d sine theta. D times sine theta. It's not, again, this isn't the calculus d this time. This is the distance d, the 1.1 meters that I was given over here. So that equals 1/2 m v final squared. There we go. And again, my unknown, the only unknown, is this one. So I guess at this point, I could just do some algebra. I want to multiply by 2 and divide by m to get v final by itself. I'm going to put that on the left just so I have it. V final squared is going to be multiply by 2 divided by m everywhere. That gives me k spring over m L squared, 2 over m times this, minus 2 over m times this, 2gd times the sine of theta. That's my v final squared. And again, at this point, I guess I could just take a square root of both sides and say that that's my victory right there. I can declare victory. Square root of both sides gives me something where I can plug it in, and that is my v final. That's going to be my final speed. Let's see. Here, v final is this. It's that square root. I can plug numbers in, and let me just do that. Let me put in some numbers to make sure that my units work. Again, I'm not going to do the calculator in front of you because that seems boring, but I'll check the units at least. K spring is 150 kilograms per second squared, divided by my mass, which is 0.10 kilograms, times 0.05 meters squared. All that minus, I have not left myself enough room by a long shot here, all that minus 2 times 9.8 meters per second squared times my distance of 1.1 meters times the sine of 7 degrees. And this is all under a square root sign in there. That's my deal. Let me check units, see where that goes. Kilograms cancels with kilograms, so I've got meters squared per second squared in the first term. That sounds promising. My second term is meters per second squared times meters squared per second squared, so I can subtract them, and the square root of meters squared per second squared is indeed meters per second. So when I do that, again, if I do the calculation on my own without making you watch me punch the numbers into a calculator, I end up getting that the answer here is about 1.06 I got, 06 meters per second, or maybe to 2 sig figs, 1.1 meters per second, and that's my answer. Again, I know I skipped over a lot of steps this time, but I wanted to show you that this is just the same energy calculation we did before, just slightly different, modified ever so slightly to make this, to look at this slightly different situation with the mass going up the slope. All right, that's it for this example. I'll do one more little video with a final example, changing this block to a ball, a solid ball going up a slope with friction, rolling without slipping. We'll do that next, but for now, this is just another illustration of how the same setup, the same energy setup, can get us pretty quickly to the answer to a question using conservation of energy, even a different question, just solving for different things based on what we're given in a problem. I hope that's useful.